the last lecture we solved a minimization problem using the simplex algorithm, and we introduced artificial variables when they were necessary. We also indicated that the greater than or equal to constraint, because it has or gives a negative slack, will try to introduce an artificial variable in the simplex algorithm, and we also said that we have to reduce the number of artificial variables introduced in the problem because they do not exist in the problem. There are some other aspects of initialization that we will see in this lecture. We then go on to look at some aspects of iteration and termination with respect to the simplex algorithm. Now, what are the various aspects of initialization that we have to see? One, we have to look at the right hand side values, we need to look at the variables, objective function and constraints. Now, let us consider each one of them. Right hand side value of every constraint should be non-negative. We have already seen this. It is actually a rational number. If it is negative, we have to multiply the constraint by a -1 to make the right hand side non-negative. The sign of the inequality will change. If there is a less than or equal to, it will become greater than or equal to, and vice versa. That is the only thing we need to look at. Or what we need to ensure is, when we start the simplex table, we have to make sure that every constraint has a non-negative value in the right hand side. Next thing we need to look at are the variables. The variables can be of three types, as we have already seen. We could have greater than or equal to type, less than or equal to variable, and an unrestricted variable. We have seen formulations that involved greater than or equal to. Most of the problems per se will have greater than or equal to variables. Very few instances we might have an unrestricted variable. We have seen one formulation which had an unrestricted variable. Less than or equal to is very rare, and we include it only for the sake of completion. Now, we also know that when we start the simplex iteration, all variables have to be converted to the greater than or equal to type. We cannot have unrestricted or less than or equal to when we start the simplex iteration. So, what we do there? Of the three, the greater than or equal to is desirable. If we have the less than or equal to type variable, we replace it with another variable of the greater than or equal to as follows. If a particular xk is less than or equal to 0, then we replace it with another variable xp equal to minus xk, and xp will become greater than or equal to 0. This change is incorporated in all the constraints as well as in the objective function. So, it is very easy to handle if a variable is less than or equal to type. Objective function can be either maximization or minimization. There is also one more thing before we do, is we need to check what happens if the variable is unrestricted in sign. Go back to the previous slide. The variable can also be unrestricted in sign. So, when the variable is unrestricted in sign, what we do is the following. If we have a particular xk unrestricted, we replace xk by two variables. You can call them xk dash minus xk double dash, or you could be some xl minus xm. We replace every unrestricted variable with two variables xl minus xm or xk dash minus xk double dash, and incorporate this change in the constraint as well as in the objective function, with the additional condition that xk dash and xk double dash both are greater than or equal to 0. Now, if this unrestricted variable is in the solution and takes a positive value, then this will be in the solution and take a positive value. If this is in the solution and has a negative value for the given problem, then this one will be in the simplex table and this will take a positive value, so that the net will be this negative. If this is not in the solution of the original problem, then both will not appear as basic variables in the simplex. We will see this later through an example. Now, let us now go back to the two types of objective functions. Objective functions can be either a maximization function or a minimization function. So far we have solved problems of both. We have solved maximization problems as well as one minimization problem. The standard thing to do is to convert the minimization into a maximization by multiplying the objective function with a -1, convert it to a maximization problem and solve it. So that consistently we can use the largest Cj minus Zj as a rule to identify the entering variable. Constraints are of three types: greater than or equal to type constraint, less than or equal to type, and equation. If a constraint is of the less than or equal to type, this is assuming that the right hand side values are non-negative or after converting them to non-negative values. If a constraint is of the less than or equal to type, we add a slack variable and convert it to an equation. Slack variable is a positive slack variable. If the constraint is of the greater than or equal to type, then we add a surplus variable or a negative slack variable and convert it into an equation. For example, if we have a constraint x1 plus x2 greater than or equal to 7, then we write x1 plus x2 minus x3 equal to 7. This minus x3 is a negative slack variable. And then this minus x3 being a negative slack cannot qualify to be an initial basic variable. Therefore, we may have to add artificial variables. So, if necessary, we add artificial variables to identify a starting basic feasible solution. We illustrate this through several examples. Let us take the first example, which is like this. Now, the first constraint is an equation, second constraint is a greater than or equal to type inequality. Already the right hand side values are non-negative, the variables are greater than or equal to 0, the objective function is maximization. We do not need to do any of the conversion to the standard form that we are comfortable with. Now, we have to look only at the two constraints. 2x1 plus 3x2 is already an equation equal to 7, 5x1 plus 2x2 is greater than or equal to 11. Now, this greater than or equal to inequality is now converted to an equation by adding a negative slack. So, we have 5x1 plus 2x2 minus x3 equal to 11. Now, we write the matrix form 2, 5, 3, 2, 0, minus 1. Corresponding to variable x1 you have 2, 5, corresponding to variable x2 we have 3 and minus 2, corresponding to variable x3 we have 0 and minus 1. Now, we do not find any identity column there, or we do not find any variable which can qualify to be a basic variable. So, in this case we need to add two artificial variables a1 and a2. So, first one will become 2x1 plus 3x2 plus a1 equal to 7, and the second will become 5x1 plus 2x2 minus x3 plus a2 equal to 11. And then we start the simplex table with a1 and a2 as basic variables, and you can use either the two-phase method or the big M method to solve this problem. So, this is a case where we have an equation and an inequality, we need to introduce two artificial variables. So, let us go to another example. Let us take this example, which again has an equation and an inequality. Now, once again the right hand side values are non-negative, variables are all greater than or equal to 0, and the first constraint is an equation, so we do not do anything. Second constraint is an inequality which is of the greater than or equal to type. So, we add a negative slack and convert it to an equation to get 2x1 plus 3x2 plus x3 equal to 7, 5x1 plus 2x2 plus x4 minus x5 equal to 11. Now, we realize that the variable x3 has a plus 1 coefficient and a 1, 0, it does not figure in the second constraint. Variable x4, which is part of the problem, has a plus 1 coefficient, does not figure in the first constraint, so it has a 0, 1. Now, x3 and x4 become eligible to be the initial basic variables. So, this is an example where we do not have to add an artificial variable at all, even though we had an equation and we had a greater than or equal to. So, it is not that we blindly add an artificial variable whenever we have an equation or a greater than or equal to. The only thing we need to do is to convert it to a set of equations, see whether there exist basic variables. If they exist, we use them. If they do not exist, we add. We observe that x3 and x4 in this example have coefficients of the identity matrix, and we can start with these as initial basic variables. We need not use artificial variables at all in this case. You can also do a few things. For example, if the second one 5x1 plus 2x2 plus 2x4 is greater than or equal to 11, we can still do this and divide by 2 and make this x4, and now x4 will have a 0, 1 and we can start. So, the message that we are trying to convey through these examples is, it is not absolutely necessary to add an artificial variable for every greater than or equal to, while it is absolutely necessary to add a negative slack to convert it to an equation. All we need to do is, given the constraints, we first add these slack variables and bring it to an equation form. If we can identify basic variables from there, we start the simplex iteration using the basic variables. If we are not able to identify, only then we add artificial variables. In the process, we minimize the number of artificial variables added to a problem. Next slide. Now, these are the rules about artificial variables. Ensure that the right hand side is non-negative. If we have a less than or equal to, we add a slack variable which automatically qualifies to be a basic variable. If we have a greater than or equal to, we add a negative slack to convert it to an equation. The negative slack cannot qualify to be an initial basic variable. The system of equations, whether there exist variables with coefficients corresponding to column of the identity matrix, such variables qualify to be basic variables. Others add minimum number of artificial variables otherwise to get a starting basic feasible solution. Fewer the artificial variables, the better it is. Next aspect is we need to look at is called iteration. Can something happen during the iteration of the simplex algorithm? Now, we try to understand that using a different example here. The example is to minimize, to maximize four x1 plus 3x2 subject to 2x1 plus 3x2 less than or equal to 8, 3x1 plus 2x2 less than or equal to 12, x1 x2 greater than or equal to 0. So, we have less than or equal to constraints. So, we add slack variables and we write slack variables automatically qualify to be basic variables. So, we have x1, x2, x3 and x4 are the slack variables. So, I would get plus x3 equal to 8 plus x4 equal to 12, x3, x4 greater than or equal to 0. x3 and x4 qualify to be starting basic variables. So, we start with x3 and x4 here. So, we have 4, 3, 0, 0, 2, 3, 1, 0, 8, 3, 2, 0, 1, 12, 0, 0, 4, 3, 0, 0. Now, variable x1 with the largest positive Cj minus Zj enters. Now, to find out the leaving variable, we need to compute theta. Theta is 8 by 2, 4, 12 by 3, 4. So, we find something new, something interesting, that we are not able to find a unique leaving variable. So far in all our examples, we could easily find a minimum theta. There was no tie for the minimum theta. Now, there is a tie for the minimum theta that we have. Now, we need to break this tie by either leaving out x3 or leaving out x4. We could do either. Right now, let us assume there is no tie breaking rule. So, we either leave out x3 or we leave out x4. Okay. Let us go to the next table. Now, let us look at what happens if instead of x3 we leave out x4. We could either choose to leave x3 or choose to leave x4. Let us assume that we want to leave x4 instead of x3 and let us continue our iteration. So, variable x4 leaves the basis. Now, when variable x4 leaves the basis, this is the pivot element. So, you have x3 here, x1 here. So, we have 0, we have 4, dividing by the pivot element 1, 2 by 3, 0, 1 by 3, 4. I need to get a 0 here. This row minus 2 times this would give a 0. So, 2 minus 2 into 1, 0, 3 minus 4 by 3 is 5 by 3, 1, 0 minus 2 into 1 by 3 is minus 2 by 3, 8 minus 2 into 4 is 0. Now this is also something which we are encountering for the first time. First time a right hand side value has become 0. Let us continue. So you have Cj minus Zj, x3 and x1 being basic variables will have 0. This is 3 minus 8 by 3 is 1 by 3, 0 minus 4 by 3 will give me minus 4 by 3, 1 into 4, 16. Now variable x2 enters the basis. Now we need to find out theta. We already have a 0 here and we have a positive number here. So this theta is 0. We still compute this theta. Remember again, we would leave out theta only when this number is 0 or negative. As long as this number is positive, even if this is 0, we compute theta which is 0. So 4 divided by 2 by 3 will be 6, and this is minimum theta which goes. Now this is the pivot element that we have. So now we have x2, x1. Now this is 3, this is 4. Now dividing by the pivot element which is 5 by 3, 0, 1, 3 by 5, minus 2 by 5, 0. Now I need a 0 here, so this minus 2 by 3 times this will give 0. So this row minus 2 by 3 times this row, 1, 0, 0 minus 2 by 3 into 3 by 5 is minus 2 by 5, 1 by 3 minus 2 by 3 into minus 2 by 5. So 1 by 3 plus 4 by 15 which is 9 by 15 which is 3 by 5, 4 minus 2 by 3 times 0 which is 4. Now Cj minus Zj would be x1 and x2 are basic, so I have 0. This is 4 into minus 2 by 5 is 8 by 5, so I have a plus 8 by 5, and this will be minus 12 by 5, and this is still 16. Now this variable enters, x3 enters, this is minus 1 by 5. I am sorry, yeah, I think there is a mistake in the computation. So this is 9 by 5 minus 8 by 5 is 1 by 5, so I get a minus 1 by 5 here. This is minus 6 by 5 plus 12 by 5 which is 6 by 5, so I get minus 6 by 5. Now all the Cj minus Zj's are negative, the algorithm terminates. The optimum solution is x1 equal to 4, x2 equal to 0, z equal to 16. Now what are the new things that we have seen in this? One, the first thing that happened was there is a tie for a leaving variable, and we resolved the tie arbitrarily. We could have left out variable x3, but then we decided to leave out variable x4. Now because we had a tie here, we also had a 0 here. The 0 came only because we had a tie here. More importantly, this problem actually has taken 3 iterations to terminate with the objective function value 16. But right in the second iteration, we have a solution with objective function value 16, solution with x1 equal to 4, x3 equal to 0, x2 equal to 0, x4 equal to 0 are non-basic. Here we have x1 equal to 4, x2 equal to 0, x3 equal to 0, x4 equal to 0 are non-basic. So right here we have the same solution which is x1 equal to 4, rest of them 0, but the algorithm was unable to terminate here. It was still indicating that variable x2 can enter the basis, whereas only here for the combination x1 x2 where x3 and x4 are non-basic, for the same solution the algorithm now is able to terminate. In some sense the algorithm is not smart enough to understand that right here the optimum solution has been reached. It is still within the boundary or capability of simplex, because simplex would evaluate in some sense non-decreasing solutions. It started with 0, it went up to 16, it did not increase, it did not go down, it did not evaluate a poorer solution than this, but it evaluated a solution which is the same, it repeated it once again. Now this phenomenon where you end up doing more iterations than what you actually have to, which has happened in this case. If the algorithm has been good enough or smart enough, it should have identified that the optimum is right here and it need not have carried out one more iteration to get the same solution and then satisfying the termination condition. Now this phenomenon where we do additional iterations without realizing that optimal has been reached, or without moving forward without any improvement and then terminating, is called degeneracy. Now degeneracy is a phenomenon that happens in simplex iterations where we end up doing additional iterations which do not add value to the problem or problem solution. Degeneracy always happens if there is a tie for the leaving variable. A tie for a leaving variable would ensure that one basic variable takes 0 in the next iteration, and the moment a basic variable takes 0 in the iteration, what will happen is this will always be a candidate to leave, because the minimum theta will be 0, and because this is the candidate that leaves, the solution will not improve. In fact, you can show that in every simplex iteration the improvement in the solution, improvement in the objective function is actually the product of the minimum theta and the Cj minus Zj. In this case the minimum theta is 4 either way if you are taken, Cj minus Zj is 4, the entering Cj minus Zj. So the product is 16, so 0 becomes 0 plus 16 which is 16. Now in this case, because of the presence of this 0 and minimum theta being 0, no matter what your Cj minus Zj is, the solution does not improve. Because of a tie in leaving variable and because of which you got a 0 in one of the basic variables, simplex cannot move forward and you end up doing extra iterations before you terminate. It can. What we will go through the set of slides where we show that this kind of phenomenon degeneracy is actually, in this example it had happened at the optimum. Degeneracy can happen inside during an intermediate iteration and it can still terminate. In fact, what will happen is, suppose for a different problem the optimum is not 16, somewhere in the middle you have got into a degenerate situation where there is a tie, and you will end up doing iterations without improving the objective function because of this 0. Now if you have to improve and then come to the optimum, somewhere in one of the iterations you will find that for a 0 here the entering variable would have a negative. So you will not be evaluating this theta, you will be evaluating the minimum theta will now become positive if it turns out somewhere in the middle of some iteration the entering column will have a negative or a 0 corresponding to the 0 here. So this theta will not be evaluated. Now your minimum theta will become positive, Cj minus Zj will be positive, product will be positive and it will move further. So if the one thing about degeneracy is it is a phenomenon that happens during the iteration. If the problem has an optimum, the problem will terminate. Degeneracy will not prevent the problem from terminating. Degeneracy will only play its part by going through unnecessary iterations which do not add value or which do not improve the objective function. Now let us see why this degeneracy has happened in this example. We have a convenient 2 by 2, so you could go back and draw the graph and see what happens to the graphical representation of this problem. So let us do that. Let us draw the graph here. The first constraint is 2x1 plus 3x2 is less than or equal to 8. So we would have 4, 0 as one point, and you could have 1, 2 as another point. So this is another point, this is, so you could have 1, 2 as another point. So your this is the first line. Second line is 3x1 plus 2x2 equal to 12. So you again have 4, 0 and 0, 6, 1, 2, 3, 4. So this is the feasible region which satisfies both the constraints. Now in a normal 2 by 2 problem you would expect 4 corner points. Now you have 3 corner points, 0, 0, 4, 0 and 0, 8 by 3. Now you can also assume that there is a 4th corner point which is actually sitting on top of the same point. Now this point is not only the intersection of these two, it is also the intersection of this and the x axis as well as this and the x axis. So there are basically more than one point sitting on the other. Now what Simplex would do is it started with 0, 0, it then identified a basis with x3 and x1, it moved to this point, but it was not able to say that it is optimum. So it tried to move to another point which is sitting on top of it, which is x1, x2, this point, and once it reaches this basic combination it is able to identify. The point is Simplex has its weakness. If the problem exhibits degeneracy, then Simplex is unable to say that every point here is optimum. It waits, it searches till it gets the correct basis for which it can say that it is optimum. So this is a phenomenon called degeneracy. Now degeneracy does not prevent you from getting a solution. If the problem has a solution, then Simplex will terminate. The only thing is, if it gets into a degenerate situation, it will go through extra iterations. Now is there a way to overcome degeneracy? The answer is actually there is no way to overcome degeneracy. One thing that we can do is, many times it is said that if there is a tie for a leaving variable, consistently choose the one with the smallest subscript. Smallest subscript rule works well. Smallest subscript rule will ensure termination, but it will not reduce or minimize the additional iterations that you will have to go through. And in any case, if the problem has a solution, even if it exhibits degeneracy, it will terminate. So degeneracy from a certain point of view is harmless. It is not going to prevent us from getting the solution. The only difficulty with degeneracy is it will end up making more iterations than what we actually need to do. And degeneracy is a limitation of the Simplex algorithm. It is not a characteristic. It is of course a characteristic of the problem. For example, if we had used a graphical method or an algebraic method, we would easily have got the solution. We would anyway get the solution using Simplex, except that we need to do one more iteration or many more iterations. And as I said, degeneracy can happen in the middle of the algorithm, and if the problem still has a solution, it will come out of degeneracy, as I said earlier, by encountering a situation where against a 0 right hand side you would have a negative value or a 0 for the entering column. So theta will not be 0, theta will become a positive value, and then you will move towards the optimum solution. So this is the only thing that can happen during the Simplex iteration, and that is the only aspect we need to touch. Degeneracy results in extra iterations that do not improve the objective function value. Now the reason is there is a tie, so the next iteration has a 0, etc. Sometimes degeneracy can take place in the intermediate stage of the algorithm. Such cases, if the optimum exists, simplex will overcome by itself and terminate at the optimum. In these cases, entering column will have a 0 or a negative value against the leaving row, and there is no proven way to eliminate degeneracy or to avoid it. Sometimes a different tie breaking rule here would have given us the optimum in less than one iteration itself, so that can happen. In this example, if we had chosen to leave x3 instead of x4 in the first iteration, the algorithm terminates and gives the optimum after one iteration. You can take it as an exercise and see whether such a thing happens. Then we will be able to get the optimum in 2 iterations instead of 3 as in this example. Now we move to the last part of the simplex, which is called termination. So we have seen some aspects of initialization and iteration. We will now see various aspects of termination. Now there are many issues that need to be looked at in termination. We have listed all of them here. There are basically 4 issues that we need to look at. These 4 are called alternate optimum, unboundedness, infeasibility and cycling. We will concentrate on the first 3. We will only briefly indicate the effect of cycling and its role. We will not do cycling through an example in this set of lectures. So we take examples to show each one of them, the alternate optimum, the unboundedness and infeasibility. So first let us do the alternate optimum. Maximize four x1 plus 3x2 8x1 plus 6x2 less than or equal to 25, 3x1 4x2 less than or equal to 15, greater than or equal to 0. Once again we have a problem with right hand sides positive, so we do not need to do anything here. We have less than equal to type constraints, so we add slack variables to get plus x3 equals 25 plus x4 equals 15, x3 x4 greater than or equal to 0, and we can start the simplex iteration with x3 and x4 as basic variables. Let us do that. One 0 25 3 4 0 1 15. So we write the Cj minus Zj. x3 and x4 being basic variables will have Cj minus Zj 0, and we will have 4 minus 0 into 8 plus 0 into 3 4 and 3. Now variable x1 with the largest positive Cj minus Zj enters the basis. So to find out the leaving variable, we need to compute the theta. So 25 by 8 and 15 by 3, which is 5. So smaller one is 25 by 8, so this leaves the basis. This is the pivot element that we have. So now x1 replaces x3, we have x1 and x4, we have a 4 here and a 0 here. Once again this is the pivot element, so we divide every element of the pivot row by the pivot element to get 1, 6 by 8, 3 by 4, 1 by 8, 0, 25 by 8. We need a 0 here, so this row minus 3 times this row would give us a 0. So 3 minus 1 into 3 is 0, 4 minus 3 into 3 by 4, 4 minus 9 by 4 is 7 by 4, 0 minus 3 into 1 by 8 is minus 3 by 8, 1 minus 3 into 0 is 1, 15 minus 3 into 25 by 8, 15 minus 75 by 8, 120 minus 75 is 45, so we get 45 by 8. Cj minus Zj, x1 and x4 are basic variables, so you get 0 and 0. Now this is 4 into 3 by 4 is 3, 0 into 7 by 4 is 0, so 3, 3 minus 3 is 0, 4 into 1 by 8 is half, 0 into minus 3 by 8 is 0, 0 minus half is minus half, 100 by 25 into 25 by 8 into 4 plus 0 into 45 by 8 is 100 by 8. Now let us look at this solution. First let us check whether this solution is optimum. Look at the Cj minus Zj's. Now the non-basic variables are x1, x2 and x3. Both of them do not have a positive Cj minus Zj. So there is no entering variable. The algorithm terminates as we know. The only difference in this case is there is a non-basic variable x2 which has a 0. So far in all our examples, when the algorithm terminated, all the non-basic variables had negative values of Cj minus Zj. So we were very sure that entering these negative values cannot improve or increase the objective function. Remember, we are consistently solving a maximization problem. Now a 0 here can do something. The 0, when we enter this 0, now the question is, do we enter this variable x2 which has a 0 Cj minus Zj, and what happens when we do so? Now when we enter this, we are very sure that if we enter a Cj minus Zj with a negative, it will bring down the value of the objective function, because the improvement is the product of Cj minus Zj and theta. Theta can never be negative. So if we enter a negative Cj minus Zj, the value is going to come down. When we enter a positive Cj minus Zj, the value will go up, assuming that theta is also positive. Now when you have a 0 Cj minus Zj, the question is, do I enter this? Now let us see what happens when we enter this. So let us enter variable x2 with a 0 Cj minus Zj. Corresponding values of theta would be 25 by 8 divided by 3 by 4 should be 25 by 6. 25 by 8 into 4 by 3 would give us 25 by 6. 45 by 8 divided by 7 by 4 will give us 45 by 14. 45 by 14 is smaller than 25 by 6. So this variable leaves. Now this is the pivot element. Now we continue with the simplex iteration. So we have x1 and x2 with 4 and 3. Divide the pivot row, every element of the pivot row by the pivot element to get 0, 1, minus 3 by 8 into 4 by 7 is minus 12 by 56, which is minus 6 by 28, which is minus 3 by 14. This is 4 by 7 and this is 45 by 14. Now we need a 0 here. So this minus 3 by 4 times this would give us a 0. So 1 minus 3 by 4 into 0 is 1. 3 by 4 minus 3 by 4 into 1 is 0. 1 by 8 minus 3 by 4 into 3 by 14. So 1 by 8 plus 9 by 56, 16 by 56. 16 by 56 is 8 by 28, 4 by 14 and 2 by 7. This minus 3 by 4 into this, so 0 minus 3 by 4 into 4 by 7 is minus 3 by 7. 25 by 8 minus 3 by 4 into 45 by 14. So 25 by 8 minus 135 by 56 175 minus 135 is 40, so 40 by 56, 40 by 56 is 20 by 28, which is 5 by 7. Now Cj minus Zj, x1 and x2 will have zeros, 4 into 2 by 7 is 8 by 7, 8 by 7 minus 9 by 14, 16 by 14 minus 9 by 14 is 7 by 14, which is half, so you get a minus half, minus 12 by 7 plus 12 by 7 is 0, 20 by 7 plus 135 by 14 is 20 by 7 plus 135 by 14, so 40 plus 135, 175, 175 by 14, yeah, 175 by 14 is, what do we have here, 5 by 7, 45 by 14, so 20 by 7 plus 135 by 14 would give us 25 by 2, which is 100 by 8. So we get 100 by 8, or this can be written as 25 by 2. 175 by 14 is dividing by 7, you get 25 by 2. Now we get the same value of the objective function, which is understandable because our Cj minus Zj was 0, even though theta was positive, it did not improve. Now once again we realize that x1 and x2, this is expected. Now in fact the same Cj minus Zj rho is repeated. Now this x5, which is a non-basic variable, now has a 0 Cj minus Zj and wants to enter. If we had entered this, then we should enter this. Now if we try to enter this, what happens? We enter this, there is only, to find out theta, there is only one value because there is a negative here. So this will be the leaving variable. 45 by 14 divided by 4 by 7 is 45 by 14 in 2. So this will be 45 by 8. There will be only one leaving variable. This will be the pivot. And if you do one more iteration, what will happen? x5 will replace, or x4 will replace x2. So x1 and x4 will be the basic variables. So if you do one more iteration, you will end up getting exactly this. And now with this you will try to enter x2 again and so on. So if you apply the termination condition very strictly, you won't terminate at all, you will get into an infinite loop. So the termination condition has to be redefined, that if you have a situation where the maximum Cj minus Zj is 0 and it tries to enter, then it indicates alternate optimum. It indicates this is optimum, this is optimum. Both of them satisfy our termination condition. So termination condition has to be rewritten by saying to take care of this alternate optimum. This problem has right now two optimum solutions as shown by Simplex. One would be x1 equal to 25 by 8, x4 equal to 45 by 8, z equal to this. Other one is x1 equal to this, x2 equal to this, z equal. There are two optimum solutions that Simplex is indicating. So this is an example of alternate optimum. Alternate optimum is shown when the algorithm terminates and there is a non-basic variable which can enter with 0. And if you enter, you do one more iteration, and in that iteration also something else will try to enter and you will switch back and forth. This is not continuous loop. The termination condition has to be modified to take care of this happening, which is called alternate optimum. Now there is one more issue. Now right here we have recognized that the alternate optimum exists. Now is it necessary to compute the other solution that Simplex can show? The answer is yes. It is always better to compute the other solution. Now two things can happen. If you look at this solution, x1, let us assume x1 and x2 are the decision variables which could represent the number of tables or chairs to be produced. Now this is a case where you produce 25 by 8 of one product and you do not use x4, the presence of a slack variable in the basis indicates that the resource is not utilized fully. So you still have some resource available with you and you make the same profit of 25 by 2. Here you produce both different quantities, end up making the same profit, use all your resources. So depending on the situation, the decision maker can either choose this solution or this solution. It will be apparent that this would be better because you produce only one product, it may be easier, you end up saving some resources, so one could do this. Something else can also happen, though not evident from this example. It might turn out that one of the alternate solutions could be integer valued. So if x1 or x2 represent products, then it would make a lot of sense to choose that solution which is integer valued, so that automatically we can implement it without worrying too much about the continuous variable. Therefore, we need to look at alternate optimum. Termination condition has to be redefined for the alternate optimum, and both the solutions have to be evaluated. Now the next question is, in the case of alternate optimum, do we have only two solutions or do we have more than two solutions? To understand that, let us look at the graph corresponding to this problem. So let us go back to the graphical method again and draw the graph. 8x1 plus 6x2 less than or equal to 25. So let us look at some points here. Say this would give us, for example, 25 by 8 comma 0, which is somewhere here, and 0 comma 25 by 4, so it is slightly more than 4, so maybe we have a point here, and this is the line. 3x1 plus 4x2 15 would give us 15 by 4, which is slightly less than 4, so it will be somewhere here, and sorry, x is 5, so this is the point, and here it is slightly less than 4, 3, 4, so it will be slightly less than 4, so your other point. So this is the feasible region corresponding to this problem. Now let us draw the objective function. 4x1 plus 3x2. 4x1 plus 3x2 say equals to 12. So I have 3 comma 0 and I have 0 comma 4, which is this. So my objective function line is like this. So what do we observe? We observe that the objective function line is actually parallel to this. See, 4x1 plus 3x2 is the objective function line. You have 8x1 plus 6x2 equal to 25 drawn here. So they have the same slope, they are parallel. So the objective function is parallel to one of the constraints. And when the objective function is parallel to one of the constraints, and if the constraint is binding, if that constraint is going to dictate the objective function somewhere, as in this case, we just moved, this is the point of intersection, this is your point, this is one of the points that you have here. Basically this is the point which is 5 by 7 and 45 by 14. So when the objective function is parallel to one of the constraints, as the objective function moves, it will actually not only pass through 2 points which are shown as 2 solutions here, it would actually touch this completely, it will touch this line and then it will move. So it is not that there are only 2 optimum solutions, but actually every point which is between this and this is also optimum. So you have an infinite number of alternate optimum when alternate optimum exists. Then why Simplex is not able to show the infinite number of optimum? The reason is very simple, that Simplex will only show corner points. So Simplex will show this point and that point. The very fact that Simplex wants to switch between these 2 solutions is indicative of the fact that every point that is in between these 2 corner points is optimum. So we need to look at alternate optimum explicitly when we are trying to define the termination condition. Alternate optimum is indicated by number 1, the optimality or the termination condition being satisfied. There is a non-basic variable with the 0 value of Cj minus Zj which would want to enter. Entering that would give the same value of the objective function but with a different solution, and we'll have this phenomenon happening. The other variable will try to enter, and if we try to enter, we keep switching between these 2 iterations. So termination condition has to be taken care and defined for alternate optimum. Second, when we have alternate optimum indicated at any point, it is necessary, it is important to evaluate the other solution as well, for the 2 reasons that we saw. One of them could save some resources. the other reason could be one of them could give us an integer valued solution. So for these reasons it is advantageous for us to try and evaluate both these. Now going back, we also need to understand that alternate optimum does not mean only two optimum, it means many. Simplex will indicate only those two corner points which the objective function line passes through, but every point that joins these two corner points is also optimum. So we have seen one aspect of termination which is alternate optimum here. We have already seen degeneracy. There are still two more things to be seen, unboundedness and infeasibility, which we will see in the next lecture.